I didn't want that. Okay, let's see here. It's too embarrassing, you guys. All right. We're starting fresh. Chapter 5. This is where we start the fun part of this course. I know we had to get through all that beginning stuff, blah, 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 blah. And my guideline here. Now we finally start inference. Okay, and so let's see, chapter 5. Oh man, I had a class yesterday and it was like I was getting back from summer vacation. That's how bad my writing was. I didn't write all week, obviously. So starting fresh. Chapter 5 is called Foundations for Inference. Yeah. Now, inference. No, excuse me. Should I close that door? Do you mind closing the door? Thank you. Now people coming late. Like, what? Inference is a word that I don't know if we use every day or maybe it's just for stats, but to infer something, we do use the word infer, right? Which means that you take some information and then you kind of use that information to kind of extend it, right? And so that's what we're doing in inference. We take sample information, right? Which we can know everything about the sample, but what do we really want to know about? We want to know about the population. So we take that sample information and we infer about the population, okay? And so that's what inference is, okay? And so inference is, is when we take sample information to infer, oh, should clean that up, to infer something about the population. Something about the population. Okay, and so here, let's see here, I'll just use a slightly different color. Infer, I'm gonna say just kind of learn, right? Not exactly, but just to use sample information to learn about the population and to kind of make an extension about the population. And so we do use the word infer, not necessarily inference, but in this course, inference is what it's all about. So inference is an umbrella term that we use, and it covers hypothesis testing and confidence intervals. So we're going to introduce those two things here in chapter 5. We're going to kind of establish the rules of the game, right? And then those same rules apply for the rest of the term, okay? And so here's where we kind of learn the rules, and then we extend them to different scenarios, different question types, okay? Which are really going to be different data types, right? Depending on what type of data you have, right? At its core, is it numerical or is it categorical? We're going to start with categorical, okay? Move on to numerical. But inference, and this is why it's the best part of the course, is because inference is the moneymaker, okay? This is why we do statistics. This is why you have to take statistics, is because if you want to prove anything, right? Say that this drug that I developed is significantly better than this other drug, right? Depending on what you're measuring. To be able to say that, you need statistics to be able to say that, right? I looked at this many samples and I found that this difference was significantly different. So that's where we're headed, okay? So that's why it's a huge moneymaker, okay? It's all about the money, I guess. I don't know. It's a selling feature. All right. So in chapter 5, we learn kind of the rules. In chapter 5, we learn the rules. I'll say rules of the game. Okay. We're going to do, so in inference, like I said, inference is an umbrella term, right? As soon as we're taking sample information and doing something to learn about the population, that is inference, but there are two core things that we do. And so the first thing is we build confidence intervals, which I sneakily made you do already on the quiz. I didn't call them that, but when we capture the central 95%, that's a confidence interval. Okay, and we'll get there. And followed by hypothesis testing. Hypothesis testing is kind of a bigger, more formal way of establishing a significant difference, for example, right? And confidence intervals can be used in the same way, but they're kind of more informal. Okay? And so here, these are both under the inference umbrella. So what we're going to do is, let's see here. You know what? I'm just going to grab this outline. Oh, dang. Okay. I want here. So just so you know where we're headed, move this down. Okay. Here in chapter 5, and we don't need the page numbers, obviously, but here in chapter 5, okay. Today we're going to talk about point estimates and sampling variability. Okay, so that's what we're going to build on, okay, and establish some key terms and just kind of key concepts, right? Thursday we're going to look at confidence intervals, and then hypothesis testing usually takes a couple of days to get through all the rules. There's so many rules, right? But once you have these rules under control, right, then those same rules apply for chapter 6 and chapter 7 as well, right? And so here, right, these are kind of the basic rules, and they're going to apply to chapters 6 and 7 as well. And it goes on into 8 and 9 as well, but we usually don't have time to get there. It's for probably regression with Claude if you have to take it, which I think you do. Okay. So the basic rules will be applied in chapters 6 and 7. Okay. So here we start just kind of using a single proportion to establish, okay, how does this thing work, right? And then we move on to, okay, we've got categorical data. So there are different ways that we could have categorical data, right? I could have a single, so one sample proportion, right? So I have one sample, I've got a proportion, I want to compare it to some value, right? Is it less than 50%, right? Is it more than 50%, right? Did significantly more than 50% vote for Obama, just because I'm over all the Trump ones. Biden, I guess, let's talk about Biden, the forgotten president. He was so cool, but now you don't hear anything. Maybe it's a good thing. Keep it on the down low. Anyways, or maybe I'm just not watching the news like I used to be. All right, that could be it too. Okay, so here for categorical data, right, we're going to be dealing with proportions. Okay. So a single proportion, or then the next day we talk about, okay, well, what if I have two proportions? So now I have, it's hard to get away from the voting examples, especially when we're talking about proportions, right? And so did a significantly higher proportion vote for Joe in the student elections? I don't know, right? Then Emma in the student elections? I don't know, I'm just making these up. Okay, so then we have two proportions. Then we move on to, well, what if I have more than two proportions? Okay, and so then there are two ways that we can do that. So testing for goodness of fit is a way to deal with more than two proportions, right? And independence is when you have a two-way table like this. Anyways, we'll get there, okay? But we just kind of build on. So a single proportion, two proportions, more than two proportions. And then we've exhausted all the things that we can do with proportions, right? And then, so here in chapter 7, now we move on to numerical data, or we will, which means that we're going to be analyzing means. So the mean of something, right? Is the average response time for this drug significantly faster than the previous drug, for example, right? And so again, we start with one sample mean, and then we have a little sneaky one here, paired data. So that's when our samples are paired, okay? They behave in a special way, but we have two samples, but they're paired. We'll get there. And then just two independent samples. I want to compare their means. We are actually not going to, I like to pretend that we did 7.4. So if anyone asks, oh yeah, we did power calculations, we're not going to. It doesn't serve a purpose for the rest of the course anyways, so we don't need it. Okay, and then one mean, two means again, and then many means, so more than two means, right? And so what's going to happen is all of these are different question types. Okay, so these are different question types. The reason I mention that now is because it's going to be so important when you read a question, right? It'll be fairly obvious that I want you to do a confidence interval or hypothesis test, right? But which one, right? And so as we go through these, I want you to really pay attention to, okay, how is this question phrased? Because then you'll be able to pick up on what question type it is. Once you've decided what type it is, then you'll be fixed on a certain kind of block on your formula sheet, and then you can just kind of go from there, right? But that's the hard part. So basically what's going to happen is chapter 5 is 6.1 just built out like crazy. Okay? So we just kind of do it again in 6.1, which means I kind of gloss over it a little bit, okay, and then move on to 6.2. Okay. So I think we're ready. 5.1. So that's where we're headed. That's basically up until April, the end of March, right? That's what we're going to be doing. And then we start regression, which is a super fun thing that you might have seen already, but we kind of just, I like to end on a high note. It's like, oh, okay, phew, something easy again, right? Or maybe for the first time. So I like to end on that kind of easy street. So 5.1 is called point estimates and sampling variability. Yeah. First thing I want to do is just establish what a point estimate is, and then I'll show you with a kind of a brief example. So a point estimate is some information from our sample, right, that is kind of the miniature version of the population thing I'm interested in, right? So for example, the sample proportion is my point estimate for the population proportion, which I'm actually interested in, right? And so it's basically our best guess at what the population thing is. And I'm being vague on purpose here because it can be a lot of things. Okay? But a point estimate is information from a sample I'll say that will serve as our best guess for what the population looks like. That will serve as our best guess for what the population looks like. As a quick example, right? And this is going to happen a lot when we talk about proportions. The main proportion that a lot of companies are working on is voting predictions, right? It's kind of where we got started and we're there, right? There's a lot of, everyone wants to know. They can just go vote and wait, but they don't. So to predict who will win a presidential election, what would we do? We could collect a random sample of, I don't know, 100 US adults, right? Canadian, but it's too boring. Right, so US adults, and because their elections are always way more fascinating, right? It's crazy. What would we do? We could collect a random sample, ask them who they're voting for. Sure, there's bias and things like that, but if we've randomly sampled and we just assume that they're telling us the truth, right? Then we use that proportion, that sample proportion, and we can say, okay, well, based off of this sample, I think 40% are going to vote for Kanye. No, I don't know. I know, right? Scary. Who knows? Those guys, they're crazy. All right, so we collect a sample, right? We ask them and we get some proportion in favor of whatever candidate we're talking about, right? What if you let those guys go, those 100 people go, and you collect a new random sample of US adults, right? Do you expect that sample proportion, right? You do the same thing over again, just in theory. Do you expect that sample proportion to be the exact same as the previous one? No, right? So then, okay, then we have this kind of movement around the true population proportion, right? And so that's where the sampling variability comes in, right? So we need some way to say, okay, well, yeah, I took a sample and I understand that it moves around a little bit, right? But what's going to happen is it moves around a little bit in a normal distribution. Okay, so they're all kind of hovering around the population proportion, and then you might have some stragglers, but we'll be able to use the normal distribution to figure out kind of the spread of these values. Okay. So that's kind of the key, is to remember, okay, well, this is a sample, but it can move around a little bit. Just because I have this sample value, right, doesn't mean that that's the truth. I could have gotten a weird sample. We don't know that, right? But it can happen. Okay. So to predict who will win a presidential election, we could collect a random sample of 100 US adults and ask which candidate they're voting for. So now let's just keep in mind that the US adults here is your population. All US adults. You have a sample of 100 US adults, right? But the US adults overall, that's your population, and the 100 US adults is your sample. But notice how your sample has to match your population, or sometimes we call it our target population. And so if we find, sure, let's say, if we find that 14 people say they're voting for Kanye, is he running? Has he declared? He keeps threatening to, and then, I don't know. Who's another obscure one? Anyways. I know, but 14, I wish. 14 people say, you know what, I'm gonna do it. They will vote for Trump. It's even funnier if Trump is not running. Like,
I think it's really funny is that there's been shits made of like him running and then all of his family members running, but like they did the math really bad, and so they had it on the wrong years and stuff.
Of course. I feel like that's pretty on brand, actually. Yeah. They're like, we're gonna run the White House. Okay. So 14 people say they'll vote for Trump, right? So the point of it is what will be 14 over 100. This is a sample proportion. Okay. Sample proportions are denoted by p hat. Okay. So then p hat, I'm putting it down before I've defined it here. P hat is the sample proportion. So it's just the lowercase p with a hat on top, and it's called p hat. Oh, and that's when this textbook, she cracks me up. She's so funny. Oh, whoops, that's not what I wanted to do. I wanted to actually go here. Where does she have it? Oh yeah, okay, so it's on page 170, where she introduces p hat, and then she has a little subscript that says not to be confused with pH fat, the slang term used for something cool like this book.
Oh, cute.
We used to say that a lot, but I know I'm a lot older than you guys. So anyways, yeah, pH fat. Yeah, she kind of boiled it down a little bit. Yeah, because I think it was something a little bit wilder. Or maybe I don't know. Maybe I didn't know. But anyways, pretty funny. Something cool like this textbook. All right. So that's your p-hat. Okay. And so this is going to be your point estimate. What's it estimating? It's estimating the population proportion, right? And we're going to denote the population proportion by just the lowercase p. Okay? I know I'm saying a lot and not writing a lot. So let me catch up here. So this is the point estimate for the proportion of all US adults who plan to vote for Trump. Okay. So it's a point estimate for the proportion of all US adults, which we will denote by, we denote the population proportion by a lowercase p, or if you want to, you can use pi, because typically, right, we use Greek letters for parameters, which are anything that measures a population, right? And so, or pi, but I use lowercase p, just so you're not kind of confused. But a lot of upper level textbooks will use pi. But pi is that irrational constant, so it gets kind of confusing sometimes. But if you want to stick to the Greek letters for populations, you can use pi, but I just use p. Okay? And it's the only time that I use just a regular letter for a population. Okay, and so, right, p-hat is our best guess for what p is. Okay. Okay. P-hat in general is going to be x over n. I can't remember if I typically don't put p-hat in your formula sheet. I expect you to know how to get there, but x is the number of successes over the sample size, right? N is still the sample size. And luckily, we've already seen these successes before in the binomial, right? In the binomial section, which I know was a long time ago now, right? But we've seen successes. It's whatever you're interested in, right? Who's voting for Trump? That could be a success, right? Who's voting for Obama? That could be a success, right? It depends on the question. So the number of successes, right, comes from the question, but then you can use that to find your p-hat. Okay. Kind of went off script here, so let me make sure I didn't skip anything. Okay. So in this case, we found that p-hat is 14 over 100. So p-hat is 0.14. Now I'm going to move that down here. Okay. And the reason I'm going to move that down here is I just want you to remember that the rules for proportion still apply, right? A proportion has to be between 0 and 1, right? And so proportions must be between 0 and 1. just as a reminder. Okay? You can use the fraction if you want, or convert it to a decimal. Usually I convert it to a decimal. Okay? But this p hat, right, 0.14, is our best guess at how the entire population feels. Okay? So p hat equals to 0.14 is our best guess as to how the entire population feels, or as to how the entire population I'll say will vote. Yeah. So that means I'm expecting about 14% or 0.14 of the population to vote for Trump, even if he's not running. So, which makes it funny. All right. So, like I said, we understand that if we return our sample back into the population and then we randomly sample from all US adults, right? Yes, in theory, I could select the same person again. That's okay. The probability of that is very, very, very low, right? 100 people from all US adults, right? So it's not a huge concern. Is that a question or a resting hand?
So obviously like 100 people is not large enough to be reflective of the US voting mass. So what's kind of like the cutoff? Because obviously like if we were looking at 200 people, 100 is well more than enough. So where's that kind of, you know what I'm getting at?
I do.
Yeah.
And I'm about to say it
Oh,
in about one paragraph. Yes, I do know what you mean. So stay tuned because I'll get there. I'm like, I'm this close. And it's funny because you want to have a large enough sample, right, to be representative. But then there's another condition that we're going to ignore is that you don't want to have too big of a sample because then you lose the independence. So it's like you want it to be big to be representative, but you don't want it to be too big because then it's not independent anymore, right? Then you're selecting people in the same household if you're selecting in the States or something like that. And so there's a fine balance. We ignore that upper one because we say the bigger the better, but technically there's an upper bound as well. Okay, but what I wanted to highlight before I talk about that is, right, if we collected a new sample, right, we understand that that proportion would change. Okay, so if we collect a new random sample of 100 US adults, we understand our sample proportion would change or would likely change but on the flip side, right, so we understand that it would be different, right? But what would be weird? What if you found a sample proportion of 0.2? 0.2 is quite far from 0.14. We don't know the spread, but right, we also expect these sample proportions to be hanging out in the same neighborhood, right? And so however, we expect the new sample proportion to be close to the previous sample proportion. Oops. Yeah. So to summarize this variability, we rely on something called the central limit theorem. And it is exactly as important as it sounds, right? Something called the central limit theorem sounds important, right? And it is, okay? But for now, we're just going to use it. Okay? So to summarize, oops. So to summarize the variability, right? Variability is that, okay, if I collected a different sample, it would change a little bit, right? So there's variation between the samples. So that's what I mean by to summarize the variability, okay, of p hat. We rely on the central limit theorem. Which is abbreviated CLT, central limit theorem, and I'm just going to grab it and talk about it. So in the textbook, she does have some R code to just walk you through the idea of the central limit theorem. But for us, like I said, I'm just going to go for it. Ooh, that's a lot. All right. Okay. So the central limit theorem and the success failure condition, which is going to answer your question. So let's just read through this, and then I want to break it down into different components. So when observations are independent and the sample size is sufficiently large, the sample proportion p hat will tend to follow a normal distribution with the following mean and standard error. Now, we haven't talked about standard errors, but I will. Okay, but for now, just kind of take it as it comes. Okay, so the mean of p hat. So notice how we use a little subscript p hat to denote that, hey, this is the mean of p hat. Okay, is just p, is the population proportion. So it's going to be centered around the population proportion, which if I asked you, right, hey, here's my sample proportion, where do you expect it to be hovering around? Well, probably the population proportion, right? Assuming you took a random sample and it's all representative and it's all good, right? And so that's not really a surprise. The surprising part is that a categorical variable can follow a normal distribution, which we've already seen, right? But then we have the standard error of p hat, which is the square root of p times 1 minus p over n. And again, I'm going to break this all apart to 4 or 5 pieces, I guess. In order for the central limit theorem to hold, the sample size is typically considered sufficiently large when n times p is greater than or equal to 10 and n times q is greater than or equal to 10. We've seen this before, right? We saw this when we had to use the normal approximation to the binomial, right? P is basically a binomial situation, right? But now we're using it in a different sense, okay? Because I want to know, okay, what's the variability about P, or P hat rather. And so, but the same rules apply, okay? But the spread component is a little bit different. Okay, so where do we start? Let's start at the top. So when observations are independent, I'll start there. this is really saying, right, if the observations are randomly sampled, right, then we can assume independence, because that's what randomly sampling does. Okay, and so if, and maybe I'll use a punchier color here. If the observations were randomly sampled, we can assume independence. Now I know in your overactive minds, you're thinking, well, that's not necessarily true, right? What if I randomly selected siblings and they feel the same way about voting? Well, the likelihood of that is very, very low, right? And so when we randomly sample, that's when we can say, okay, I've randomly sampled, so I now am allowed to assume independence. Okay? And so this makes it a condition, right? So one of the conditions that we're going to have to check is, okay, did I randomly sample? Which we've already seen, right? So nothing new yet. And the sample size is sufficiently large. So the next one we're going to tackle. Okay. Let's see here. I'll snag it from the bottom. Okay. So here, right, if, I'll just write it out, n times p is greater than or equal to 10. Oops. And n times q is greater than or equal to 10. Right. Just as a reminder, right, where q is my shorthand for 1 minus p. Saving myself 2 characters. It's pretty good. We've seen this before, right? N times p is, in this case, the expected number of successes. Okay. And so here, generically, I'm just going to call it the number of successes and the number of failures, because it's going to change depending on what we're doing. Number of successes and the number of failures, which kind of alarmingly means that, again, your minimum sample size is 20, right? If the proportion is 0.5, right? If there's a 50-50 split, which is rare, right? Then you need a sample size of 20. Anything kind of discombobulated, right? 0.4, 0.6, that's going to require a slightly larger sample size, but it's a relatively relaxed condition, okay? Meaning that it's easy to achieve. Okay? And so, right, we need these at least 10 successes and at least 10 failures. And in our little example, right, we had 14 successes, which means we had 86 math, right? Failures, who knows, right? And so both of those conditions would check out. Okay? So this is the success failure condition. Okay? I'll also add, only because in some, I'll post some examples and some problems from way before when I used to include this condition. And so I'll mention it here, and then we're just going to ignore it. I don't expect you to remember it, but another condition is the 10% condition. Oops. But we will ignore it. I'll say this term. I just don't want you to be kind of thrown off if you see it. The 10% condition is that the sample size has to be less than 10% of the population, right? And so that's how you ensure that you're not taking too much of the population. That's really only a concern if you have a small population, right? Then you don't want to take too much of it in your sample. It actually works against you, which is counterintuitive, but so it is. Okay, so 10% condition, sample size should be less than 10% of the population size to maintain independence. But like I said, we will ignore this term. So you don't have to worry about that one. Just focus on these two conditions, right? Independence and then the success failure condition. Okay, why do we care about this? Well, it says that, okay, if these conditions are satisfied, then the sample proportion, p hat, will tend to follow a normal distribution with a mean of p and a standard error of the square root of p times q over n. Okay, and so that's what we're going to use. So if these conditions are satisfied, the central limit theorem says, oops, that p hat is going to follow a normal distribution. So here's that notation again that we saw before, a normal distribution with a mean of p and a standard error of pq over n. So we saw that mu of p hat is p. What we didn't talk about is the standard error of p hat. This is usually the spot where we put the standard deviation, okay? But because I've collected a sample and there's a lot going on in the background, but for a statistic, okay, so not just one observation, but for a statistic like p hat, then the standard error is just a different name that we use. It is the standard deviation, but it's for a statistic. So the standard error of p hat is the standard, maybe I'll do it properly. The standard error of you know what, I'm going to swap those. Sorry about that. The standard deviation, I'll start from the other side. The standard deviation, which is what we usually have here, right? Normal, mu, sigma is how we usually write this notation. So the standard deviation of a statistic, often I'm redundant and I say sample statistic. Why is that redundant? A statistic is from a sample, right? A parameter is from a population. but sometimes I just do it to emphasize, but here I've written it above. So the standard deviation of a statistic is called the standard error. Okay. So it's okay, it's just the spread of p hat. So therefore, the standard error of p hat is the spread of p hat. Oops. My hats aren't looking that great. There we go. What's kind of a major problem that we're facing here? Our whole goal was to use p hat to learn about p, but now we're saying, okay, well, if you want the mean and the spread of p hat, you're gonna need p. That doesn't make sense, right? And so instead of p, what do we use? We use our best guess for p, which is p hat, okay? Which means that any p hat, so now we can rewrite this and say, okay, any p hat is going to follow a normal distribution around p hat with a standard error, so a spread of the square root of p hat q hat over n. Okay? So
here P is the population, right?
That's right.
And the number of population.
Yes.
And the success rate and
Yes.
And P hat is the
Sample proportion. Yeah.
So it's basically the normal approximation of binomial distribution. I think the formula.
Yes. The only thing is that you're dividing by the square root of n because it's a statistic, but I'm not talking about that on purpose.
In our previous
So that's for the standard deviation, right? It's n-1, but here, this is how we're gonna find the standard error of p hat.
would that be also standard deviation?
Yes. But the standard deviation for a single observation, so for just a column of data, right, is going to be different than the standard error of p hat. Yeah, I know. It's okay. For now, just take it at face value and I'll show you slowly. Okay, so here, the problem is that since we don't know p, we use our best guess, which is p hat. We use our best guess, which I guess I should be calling it the point estimate. Which is p hat. Okay.
But since the P is mean of P hat, right?
Mm-hmm.
And we have calculated mean as like NP.
So that was for the binomial. Yeah, so although there's a lot of overlap, how we're going to use it behaves a little bit differently. So it's not quite the same, but there's, I mean, yeah, there's a confusing amount of overlap. And then we say, well, no, if you're doing inference about p hat, then you use this that we're introducing here.
So we cannot write mu equals to NP.
No. Okay. So using p hat instead of p, right? Let's just recap the conditions. So now using p hat instead of p, my hats look like tildes today. Using p hat instead of p, we can rewrite the conditions. The first condition is independence. That one doesn't change, right? You're gonna just argue whether the sample was randomly selected or not, right? If it was randomly selected, then you can assume independence. Here's the thing though, if it doesn't say, you're gonna say, I assume the sample was randomly selected, right? Because the condition, sometimes I'll call them assumptions, right? You're just stating your assumptions. I assume that I can assume independence because I also assume that the sample was randomly selected. And so that's confusing, I know, in the beginning, but was the sample, and maybe I'll say conditions / assumptions.
What is the word?
Rewrite, ironically. There. So was the sample randomly selected? Or assume that it was? Regardless, you're just going to argue that that condition is satisfied.
In our test and assignment, most of them will be like this.
Yeah. So here's the thing. These conditions will always be satisfied in kind of a classroom situation, right? And so unless it's one of those, tell me why the conditions aren't satisfied, then of course, yeah, you have to pick the one that's not satisfied. But in general, if I'm just asking you to do a problem, these conditions will be satisfied, right? And so you either have to assume that they are or show me that they are, right? But we just have to do it in order to proceed, right? It's more important in the real world when you're, looking at raw data. Was it randomly selected? And the success failure condition, right, was that n times p, right? It was that n times p has to be greater than or equal to 10, but I don't have p. And so what am I gonna do? I'm just gonna replace it with p hat, right? Now, n times p hat is actually the number of successes, x. Depending on what information you have in the question, sometimes it's easier to just use x and you don't have to do n times p hat because you would have had to calculate p hat. But sometimes if I only give you p hat, then you have to calculate the number of successes, right? And so what this turns into is that we observed at least 10 successes. The second condition in the success failure condition is the failure portion. Q hat is 1 minus p hat, which if you want to, you can say that's the same as n minus x, right? If x is the number of successes, then n minus x must be the number of failures. And so this is we observed at least 10 failures. Okay.
First, we take the sample from the population, and then we assume, since we don't have the population, assume that the sample is the population.
No, so close though. We just have to assume that our sample proportion reflects the population proportion, or at least kind of close, because then we can use the spread of the sample proportion to say, okay, here's a ballpark figure of what I think the population proportion might be, right? And so, yes, it is weird, but I mean, people worked on it for hundreds of years trying to develop, well, how can I summarize the spread of p hat, right? What would you have to do? You'd have to look at a ton of different p hats, map them all out in a histogram, and then you can do that over and over and over again. And then eventually you would arrive at, well, I think I can model the spread by the square root of p times q over n. How did they do that? I don't know, but they did. And here we are. Okay, so then we have then p hat follows a normal distribution centered on p hat with a spread of p hat q hat over n. Okay.
So p hat can change according to our data set, right? Because our sample size can differ even in the same population.
Yeah, so here's the thing. We only ever collect one sample, right? But we understand that in theory, I could go and collect a different sample. I could go and collect 100 different samples, right? But you only collect one, right? And so then we say, okay, I have to assume that this is representative of the population, right? Because I have no other option. But then we're going to use that to learn about the population, right? And so so this normal distribution, right? Really what we're saying is that the distribution of p hats, right? Not our specific p hat. Our specific p hat is fixed for one sample, right? Our p hat is 0.14. It doesn't have any variability around it, right? It's a future p hat, right? From the same population measuring the same thing would be slightly different. And so it would follow a normal distribution centered on p hat, whatever the p hat du jour is, and then the square root of p hat q hat over n, right? How about we do an example? And I'm actually gonna snag it from, so they do a lot of work kind of developing the central limit theorem and all that fun stuff, but this is the one that I want. Start here. So as part of a quality control process for computer chips, an engineer at a factory randomly samples 212 chips during a week of production to test the current rate of chips with severe defects. She finds that 27 of the chips are defective. Okay, so we have a sample of size 212, so we can jot that down. All right, so here, n, there's no room. Maybe I'll crop top this just a little bit more. Hey. No. Crop. There. N is 212. Oops. Uh, 27 of the chips are defective. So in this case, what do we want to know? We want to talk about the rate of chips with severe defects, or the proportion of chips with severe defects. So the defect is a success in this case, right? It's what we're interested in. And so here, right, 27 is x equals 27, the number of successes. Okay, The rest are going to be introduced in the parts. Usually I do that, I get too ahead of myself and I end up answering the questions too early. So I'm not gonna do that. If I can just crop this a little bit. Ooh, so small. What population is under consideration in the data set? Okay. So, but the population, so that's your sample, right? But it's a sample of chips during a week of production. Okay. So if I asked you to use this sample to talk about a week of production last year, you'd say, well, that's not, you can't really do that, right? I can only use a sample of 212 chips from this week, let's say whatever the particular week is. I know, I'm like, keep it together, right? I can only use this sample to learn about all chips being produced this week, right? And so that's really important. So that's our population, okay? So the population here is going to be all chips produced that week. I guess week of production, but that's okay. Maybe don't need it. Okay. So here, what this is getting at is, okay, my conclusions can only really talk about all the chips produced that week, right? I can't extend it to multiple weeks. I'd have to take a new sample just in case things have changed. Maybe this cropping is too slow. I'm getting better though. What parameter is being estimated? Oh, sorry, I hit it. Okay. It's the proportion of all chips produced that week with a defect, right? And so P is the proportion of all chips produced that week that had defects. Pretty good. What is the point estimate for the parameter? The point estimate for the parameter is your p hat, right? P hat, which is x over n if you want to start from the beginning, right? But p hat in this case is going to be 27 over 212. You don't have to try to be a hero and work with fractions. I usually just get, I don't know, 4 or 5 decimal places and go with that. That's fine. And so p hat is, and this is just from my notes, but hopefully they're right, 0.1273584,906. You'll have to use your judgment, but you can usually round this to about 4 decimal places. Okay. Unless, of course, you have a ton of zeros. You want to keep as many zeros as you have to keep information. Okay, but so here I'll just say usually rounding to 4 decimal places is safe. So then I'm gonna say that p hat is 0.1274. Looks like I got lazy in my notes and I used just 0.127. Wow, that is lazy. I'll have to do the calculations. All right. D. What is the name of the statistic we, oh, a typo. We can use to measure, right? Can we use, no. What is the name of the statistic we can use to measure the uncertainty of the point estimate? Not a hard question, it's just written in a weird way. Must have made a change or something. That's gonna be the standard error of p hat, right? So the uncertainty of the point estimate is the standard error of p hat. Oops. Finally, pretty hand-holdy question here. Compute the value from part D for this context. Okay, this is where I saw I had used a sneaky version. The standard error is P times Q over N, but I don't have P and I don't have Q. So I'm gonna use P hat Q hat over N. So this, I'm writing it nice and big here. This is where I would use the rounded value. So P hat is 0.1274 times 1 minus 0.1274. Should extend that. Divided by N, which is 212. And just gonna do it just in case something changed. Don't forget your square root. What happens if you don't take your square root? You have a huge spread, right? Which would mess with your values. 1 minus 0.12274 times 0.1274 divided by 212. Square root that. Bada boom, bada bing. 0.022899,415. As a rule, I would say just try to match the number of decimal places, right? So if you use 4 earlier, use 4 again. So 0.0229. I know I'm cutting it close, but I want to finish this example. And I'm getting so good at cropping on the fly. The historical rate of defects is 10%. Okay? We had roughly 12%, right? Almost 13. Okay, so now we're saying, okay, the historical rate of defects is 10%. Should the engineer be surprised by the observed rate of defects during the current week? Cuidado. The spread, right? So what do we have to do? We have to take into account the spread that we just found, right? It's only rare if the spread is super, super small, right? If you have a huge spread, then it's not rare at all, right? So that's where we're back to z-scores, right? We have to standardize it to see how many spreads, right? Standard errors in this case, is it from 10? Yeah. So here, I'm just gonna rephrase this. It's asking, is 12.74% extreme compared to 10%? Oops. So what we need to do is we need to standardize. So I'm gonna say, okay, well, I've got 0.1274. I wanna see how far is it from 0.10 when the spread is about 0.0229. Okay. I've got 0.1274 minus 0.1 divided by 0.0229. Womp womp. 1.19650655. This is not that far away, right? It's 1.2, let's round up, standard errors away from 10%. Now, as a rule, we say that anything beyond 2 standard errors away is going to be considered extreme, okay? But I was so close to finishing this example. There's only one more part. As a rule, a value plus minus 2 standard errors from another value is considered extreme. Okay. Since 0.1274 is 1.197 standard errors from 10%. Oh man, mixing up my units here. From 0.10, it would not be considered extreme. Now what I'm gonna do, because yes, I am out of time, I am going to just leave this here so we can start on it. It'll be our review for next day, but I want you to try it just on your own briefly. It's just getting you to use the actual P of 10% and to see how it changes the spread. What you'll see is that there's not a huge spread or a huge difference in spread. Okay, if you have any questions, let me know, but I'm gonna stop this recording here.